So, so basically, your corrosion factor is a function of your hardness. Okay. However, you can see it's not a linear. So if your hardness is high, your corrosion factor will be a little bit low. Okay, and they are always less than 1. So make sure we cannot amplify your modulus, but this correction factor is associated with the hardness. Second, if we consider a circular surface of like the isolation barrier at one top, and also let's say we assume your kappa is 1. Okay. So due to that round shape, the shift factor S that's equal to D divided by 4 times T. If you want to know the elastic modulus for the actual direction that can support delta, then that EC you're going to use will be original the modulus, just like we list here, times 1 plus 2 kappa is equal to 1, so times S squared. Okay. If you want to improve, because this equation we don't consider any metal shim, if you want to improve the metal shim together, then the modification you can make, that will be 1 over EC is equal to 1 over this one. Let's say this much G. Okay. Then plus 1 over K. This K is provided by your total metal sheet. Okay. So looking at this equation, you will know because we use 1 layer of rubber, 1 layer of the steel sheet. So they are in series. So your sheet and rubber in series. The shape factor can also account for your shear stress. The relationship they just derived from theory. You average the actual strength times 6 times your shear factor. So let's say this guy here, that's the average. So the total delta you have divided by T, the deformation divided by the thickness. That means your shear stress out. And also the rotational circular shape, then the coefficient here, it's a 2/3. If there is different type of shapes, then you will have different number you have to put in. And in this equation, we only consider its incompressibility. You don't have to remember any questions here, but you have to know first what do you get from the material table. You cannot directly use in the design, okay? Because it's related to the hardness, it's related to your shape factor. Second, your actual deformation will also contribute to the shear direction. Okay. Third, your rotational modulus is also related to the shape factor, and these two numbers, they are different. Stability. Okay. This stability is quite simple. So originally, it's, for example, you look at it from the side, it's more like a rectangle, the rubber barrel. Okay. After you apply some lateral force and also the axial force, then the deformed shape will be like this one. So we made one of the corner as the support, and in the diagonal one, the corner here, we apply the vertical force and also the lateral force. Use this diagram, then we can determine how large of this delta can introduce the stability power. Okay? So the idea is that P times this arm, if the rotational center we consider that's here, okay? So this force that will be doing the clockwise, counterclockwise moment about this point. So that will be the width minus the delta max. Okay. That will be equal to this guy. You apply the lateral force. That will be doing the clockwise moment about this point. And another FH, we can use the pH horizontal stiffness, small h, times the allowable strength times that the height of the rubber barrel, right? So that's the allowable displacement in the lateral direction. That's it. Next. Times the SMH. So the delta max. means you cannot exceed this horizontal deformation. So typically it's basically the idea is that this guy is leaving until the rollout point, then it will be deferred. Okay. So here that's the critical point. You cannot exceed this delta maximum. Okay. And starting from or after that delta maximum, that's for the unstable behavior. Or rotational behavior. When you have the moment applied to a single barrel, you will, for example, introduce or induce like a KR, the rotational stiffness. So you use the rotational modulus I S divided by TR. Okay. Then this S that's coming from the steel machine plates. Okay. Then the modification is that if you consider that the overall I together, then it will become like this. So that the IS will be I times H divided by TR. Okay. UKH is the same. You use shear modulus times the area contributed from the steel divided by TR, the total thickness of the rubber. That should be equal to use original the area. Times VR. So the AS is equal to A divided by TR. So what I mean here is that when you want to use, you want to include the contribution from both rubber and steel sheet, then the original equation should be modified. Okay, the way to modify it is PR squared. So the way to modify it, just like this way. For design, because when you design a building top, probably you won't directly consider the local behavior in the moment. Only the actual force will be transferred from top to the lower floors. Okay? So for the rotational behavior, what you want to do, for example, just like in regular simulation, you want to take it to the common history. Probably you may use like a rotational stiffness, or if you want to check the local behavior, you can consider this a rotational point. But for the design, then probably only this horizontal stiffness is the important thing. Stability, okay? Basically, that's based on the buckling. We won't derive any buckling equation here. I just list the equation for you. So why we need to consider the buckling? That's also a stability parameter. So when we say stability, you do have the blowout problem, or you do have the buckling problem directly on the isolation barrier itself. So that can determine the maximum force you can apply to the rubber barrier. Okay? So they are saying if there is a derivation, your PCR, that will be this one. PS squared plus 4PSPB. Okay. And this one will be simplified to this equation, because your PS PE is much greater than PS. Okay? So the PS is that the shear force you apply to the barrier. Then PE is that the elastic buckling force. So because that's a shear force, so G times AX. Okay. Then PE, then use it's a pi squared PIS divided by H squared. So before, these two guys were deriving the equation, okay? Then this guy here is only considering the bending behavior. So the plane remaining in plane. And however, the currents he was considering the shear force directly on that surface. Okay? So the difference is that if you look at the shear force here, it's perpendicular to your neutral axis. But actually, the shear force should directly apply to the cross-section surface. So this one is right. So looking at the other one is that for the PCR is roughly equal to PS, but we are not applying this one. Okay? That's from Angus from this guy. Okay? Then when they generate the curve as compared to the theoretical derivation, then this guy is more close to the experimental result. So now we only use this one. So what you should remember is that not only consider this PS, you should also consider this P's effect. And the reason is that this one is close to the experimental result. In the design part, what do they consider first? That PCR is equal to PS times P to the square root. Then PS is G times AS. Okay. That will be G times A H divided by TR. H is total height. TR is the total thickness of the rubber leg. PE is the same. So I squared minus H squared. Then here is E. So I squared divided by H squared. Use that 1/3 BC to be conservative. So use 1/3 of BC, which is derived with the shape factor. Okay? And modify that by this one. Now, in order to simplify this equation and use the relationship between this one and this one. So we rewrite that PE we replace this BC by this relationship. So for the rest of them, you use the same. So now you can combine two of them together. G squared S squared AI ER squared. Square root of 2 I G S A times R. I will define R later. Square root of I divided by A. So for a quick example, PCR for a circular type of isolation bearing on the rubber bearing. Square root of 2 pi G times S divided by PR. So A times R for a round shape. That's IB cubic divided by 16. Your critical stress divided by A. That R. Just give you an idea. So, due to that effect, so when you move your isolation bearing, first the displacement in the horizontal direction is not small. So you move this one, then you do the projection to the effective area. That's just part of it. So that means it could be when you have like a horizontal stiffness or vertical stiffness, they will relate it to the force you apply in the other direction. Okay? So if you consider that the P delta effect, so your horizontal stiffness, that will be a function of your applied load in the vertical direction. That will make sense. Okay? If you squeeze your tofu, you may change that horizontal stiffness, right? So, that equation is just like here. KH is without any force you apply. Okay? When you apply the force, then you will reduce the horizontal stiffness. Then your KH, that's your GA divided by TR. Then for the rest of them, they are the same. So when you do the simulation, you want to do the detailed simulation. Then for every step, you have to change your horizontal stiffness because your P will be affected by the vertical ground motion. Okay. order to consider the vertical effect and also the rotational effect for the isolation guard, and also like the lateral stiffness, then people developed this very complex model to do the simulation. And the most tricky part is here. So your horizontal stiffness is not always, or let's say you can simplify to a horizontal spring. This spring is not always perfectly horizontal due to that similar to that rollout effect. So after you apply the lateral force and also the moment, then this spring will also rotate. So the spring force here that can contribute to the horizontal direction and also contribute to the vertical direction. Okay. So one of the reasons is that when you look at this one, originally the top plate that's here. Okay. In order to consider the area you can provide the shear force, then we can only use that effective area. So that will be the unit for the both top plate and the bottom plate, or here to here. Okay. So when you want to use the area for the shear force, only this red can contribute to the shear force. So your KV, remember, when we talk about the KV, then you put the metal shim and also the rubber in series. So that will be 1 over K. So your K should be EC times 8R. That's called a reduced area. AR is not a reduced area divided by H, the total height of your bearing. Okay. And also due to your shear force. And typically this term, the elastic bottom curve, this term is quite small. So it's not a shortening effect. So it will be EC times AR divided by H. So this guy is reduced area. That's this red. So for the round shape, this AR is related by S. Cosine will express them in the lateral direction divided by 2R. The diameter. So in the simulation again, you have to update your horizontal stiffness every step. You should also update your vertical stiffness every step. For design, then broadly, you don't need to consider this one and above. And by the experiment, they found use a bilinear curve, then you can, model your isolation values. So when you want to buy a LRB, you can get a category from the manufacturer. Then the numbers to create this bilinear curve, you will see in the catalog. Okay? So from the catalog, you can get a number and you can do the design. So the number you will see from the catalog is this three. First of all, a QD is this form. You use the pulse yield stiffness, okay, that's here. Then the intersection with the force axis, then that's called heuristic strength. So that will give you this number. Then Fy, of course, that's the yield, the yielding force. Then your alpha is the ratio between your linear region, this guy, the pulse yield slope divided by the pre-yield slope. So that's the pulse yielding divided by elastic region stiffness. That's the ratio. Because rubber has very small stiffness, and the recall after the yielding that the slope is almost zero, just like a PPE model for the lead. So that means the pulse yielding stiffness mostly coming from your rubber. Okay? And that the yielding force is almost coming from the lead. Remember this one mostly. So when you do the design, one of the key is that once we know your design displacement, then we can simplify this bilinear hysteresis, the model into a linear one. Okay? So use this dE and its corresponding force, then you can calculate that equivalent stiffness when you do the design. But the key again is that you have to know the dE first. Okay. Otherwise, you cannot get like equivalent stiffness. Then you cannot get the measure period you have to use from the design spectrum. Okay, so get your DB, then you can determine this stiffness, then you can calculate the nature period, then you can pick the SA you should use. Another one is that when we talk about the design spectrum, the other factor is that you have to know the damping ratio, right? So this hysteresis loop can provide a damping ratio. So we use that energy idea. Okay. So for the area of this hysteresis loop, that's equal to 4 times QD, your ED minus E1. Okay? Then when you calculate that effective damping, you use the energy dissipated by this one cycle of the area, 2 pi ES. For QD. In the earthquake engineering, they say the maximum displacement divided by the yielding displacement, that's called the ductility. So you increase the ductility, doesn't mean you increase the damping always. So in the very beginning, of course, you will increase this effective damping. But after a certain amount of the ductility, then this number will drop. Okay, so you have to remember this one. Then if this ratio, the stiffness ratio, is higher, then highly likely after a certain amount of ductility, you will see the dropping behavior. Okay? If it's a BPP, then of course you will keep increasing your damping. So let me quickly review what we learned today. First of all, if you want to do a very simple simple simulation, then you have to consider the vertical stiffness. You can go ahead and use this equation. Okay. Then also the horizontal stiffness coming from your shear modulus, and also you have to consider the rotational stiffness. Your elastic modulus should be modified due to its hardness for that correction factor, due to that shift factor. Okay, and the same idea can be applied to your rotational modulus. Stability, you have the two kinds. One is for the displacement. So that's the maximum displacement you can apply to the isolation valve. Okay. So looking at this equation, if you lower down the total height, you can increase this number. If you increase the width of your rubber barrel, then you can increase this delta max. all about your elastic buckling and also the shear force. So if you want to do the detailed simulation, then you have to consider the actual load you apply to your valve. So every time you have to update this number and change your horizontal stiffness. But actually the variation is not so high, okay? So typically this number is quite small. So if you want to do any simplification, then you can go ahead and use gauge. That's still okay. KE, what you have to remember is that there's a reduced error because at this ratio you don't have any top plate and it cannot support your vertical load. So only this reduced error that can provide that vertical stiffness. Do the design, you have to know the DD. Then you have to know how to calculate this area because you have to determine the damping ratio. Once you know the DD, you can determine the equivalent stiffness. You can find the measure period, then you can know the design acceleration you have. Then, in order to adjust the design spectrum by the BVAP, you have to know the damping ratio. Okay? Any questions? If no, then let's spend like 10 minutes looking at the high damping rubber barrel. So what's the material of the high damping rubber barrel? Probably several years ago, if you look at the TV and see the commercial, then you will see they put the material on the ground, they drop an egg, then once the egg hits the material, the egg is still there. Okay? That kind of material that can provide very high damping. So first of all, it can provide 10 to 20% damping ratio by itself. It has so nice feature, but it's still, you will see a little bit harder effect when you turn around from loading to unloading. Okay? Then, if you do a little bit of cycle first, afterwards, you can get a better behavior. Okay? So, the first few cycles, you will see this hardening effect. Afterwards, it will be a little bit stable. So, as we discussed, so when you see the maximum shear strength, for example, typically for the V rubber barrel, you can achieve 150%. do you know the idea of the 150% to 200%? Let's say the height is 0.5 meter. If the maximum strength you can reach is 200%, so that means the allowable displacement in the lateral direction is 1 meter. And it's pretty large. So, once you reach that maximum shear strength and beyond a certain range, then your shear modules will be a little bit larger. So that's harder. Okay? The strength hardening may not be good because it's more like, for example, it's a little bit more friction once you reach the hardening effect. So that's also the drawbacks of this high density rubber barrel. And the material, I guess that's also the secret of the manufacturing. So that's why you don't see so many applications for the civil engineering structures. But still, it's a very good material because you don't need to consider how to combine the V-core with that rubber again. So you use uniform material and you still do the metal shape, and you can reach what you want without that V-core. Okay? And also remember it's a frequency more like a VE, the VE material, and also the temperature effect is quite important, just like a VE for this high density rubber barrel. Okay. So it's a quick overview for the rubber barrel and all the knowledge and also the techniques to make the Lee rubber barrel is quite mature. So that's why people, for example, if you want to buy one, the company can give you the catalog. And this catalog, when you put this barrel into, for example, to the angry and to the test, you will get a percent number. Okay? So hopefully we will see more applications in Taiwan, because if you compare to the number of applications divided by the number of the buildings, and if we compare Taiwan, Japan, and also China, probably that ratio is quite low in Taiwan. Okay. All right. Any questions for today? If no, then that's all we have.